a reporter for the New York Times. And so she's up on stage, and Priest is handing her, like, here's some ISA, networking cards, and this was well after PCI had been around. Like, she's throwing those in the audience, and here's some 10 megabit, hubs and whatever, and some T-shirts, and she's throwing them out there. And so we're in the front row, like right here where you are, and she's down on the floor with Priest, and Priest reaches behind him, and he picks up a 5-slot USR rack-mountable 10 meg switch. So it must weigh like 45 pounds. It's about half full of cards, okay? And he hands it to her. She's like, "What do you want me to do with this?" He's like, "Give it away." She's like, "Can I throw it?" He's like, "I don't care." And she leans back and just heaves this switch into the crowd. So just imagine somebody sitting on the floor with a giant rack-mountable switch and just is like, "Here," And the most amazing, there were two classes of people. There were the people that feared for their lives and went away from the blast impact, and then the other people who dove to it because they wanted the thing. And so like there's this weird, and it literally hits a chair flips up and hits a guy who's coming up to grab the switch, and he hits the ground. Everyone else like jumps on top of it. It had gone right over our heads. I was like, God, I'm happy to be alive. So anyway, we will never do anything quite that dumb unless Pablos is here, and then he'll throw the podium. So. Anyway, what was the reporter's name from that story? What was her last name? 8. Who said that? Everyone's denying. Like, I didn't say shit. You get a Security University T-shirt for remembering the number 8. So, woo! I would throw it, but I'm going to knock over somebody's coffee. No, it does not have a switch in it. All right. So, hey, that's a thumbs. So this means good. Okay. You sure? Are you taping? We're streaming? All right, wow, that's great. I love it when people get to hear me stretch. All right, some announcements. All wristbands have been handed out. If you have a wristband and you're deciding not to go to the party, please turn it in to registration and we will find a friend for your wristband. Tonight in the Build It room is Inside U.S. versus Jones, a new Supreme Court decision on warrantless GPS by Marcia Hoffman. It's after the talks. Clearly after the talks. Marcia Hoffman is not going to come in and be like, "All right, I'm making my talk now." That was really funny. Parking passes are available for folks that drive in only.
Because the people who are staying here, it goes to their room.
Oh, is that why it was?
Rainbow.
Oh, I was like, that's awfully redundant. If you drove in and are not staying here, there are parking passes available at registration that get you a discount, not free parking, right? They won't let you in the what? It's full still? Oh. You got in? Did you say my other car's in there?
I said, there's nowhere else to park. The other place is closed. They said, really?
Yeah. I'll just give them this one. All right. There's parking. If you manage to land your car in there, stop by registration. We'll give you a little thing. Schedule change. John Weber is not going to be able to present today for looking into the eye of the meter. So instead, Rob Fuller is going to be talking about how he reverse DNS queried the entire internet. No lie, he did that, and he did not go to jail. Please go to feedback.shmoocon.org, enter in some feedback. And with that, you sure there's no ice cream sandwich handsets that ship? It's only the Galaxy Nexus? Really? This is why I love Android so much, is the lack of fragmentation and consistent user interfaces and the lack of crashing. Anyway. What? Heidi wanted me to throw my Galaxy Nexus down an air vent last night. That's how much we love Android. Anyway, on that note, Matthew's going to talk about Android, and I'm going to get the hell out of here. Yay! This is the part where you clap. Good luck, man.
Thanks. First talk of the morning. Good morning, everybody. Thanks for coming. My name is Matthew Raleigh. This is BlackHats Tool Chest, How We Tear in That Little Green Man. If you didn't read the abstract, it's about hacking Android applications. I'm currently a senior consultant at Modesano. I used to be a senior consultant at Intrepidus Group, where a majority of this was written and where the tool that I'll be releasing or open sourcing today was also written. Twitter handle, email up there, and the agenda, I'll do a little bit of background for a mobile application, specific analysis techniques that we use, and then a set of real-world examples, and then how all the analysis techniques are simplified with the tool. It's called Otter tool, and then questions at the end. So the first thing when looking at applications before you assess them is obviously understanding the background of how they exist in the network and what they look like. This is the, sorry, these are a little small, but this is the typical architecture that I see in my head when I am looking at a mobile application. There's two trust levels, the red on the bottom, which is the untrusted, obviously the user device, and then the top, which is the trusted, typically behind who's ever hosting this application. There's usually a typical communication flow where the user device communicates through an abstraction layer, then goes to some backend endpoint. There can be multiple backend endpoints. Usually there's some sort of authentication. The abstraction layer knows where it goes. The authentication server will respond with a token. Then it can get the data that it's looking for and be rendered to the user. There's another thing to take into account is that each one of these layers are something that you can attack. When thinking about attacking mobile applications, it's not just the device. There's also the back-end architecture that's usually associated with it. So when doing an assessment, it's not just that APK or that application that you're looking at. There's these servers on the back end that you can look at as well. An APK is obviously the file that you would install on your device. When you go to Google, or when you go to the marketplace, it downloads that and installs it locally. It stands for Android package, and it's basically a set of Dalvik bytecode and the associated resources that the application uses. When you reverse engineer an APK, there's a language that I use or a set of tools that I use called Somali and back Somali. It allows you to disassemble the Dalvik bytecode into a representation. It's similar to how assembly language looks, but it's called Somali. It is not assembly language, but there's two sets of applications that are associated with this Somali, which will reassemble the set of Somali files into a DEX file, and back Somali, which will disassemble the DEX file into a set of Somali files and allows you to view them, modify them, and then re-Somali them. The back Somali also has the ability to support ODEX, which is optimized DEX files that are sometimes distributed with OEMs, and boot class paths, which are like Google APIs that are also included with the firmware. This is an example. I was afraid that this is not going to be viewable, and I'm sorry about that. But when I learn new languages like this, I typically go to something that I know, decompile it to something that I don't know, and then try to find the linking. The arrows are basically, the left-hand side is just a simple Android activity, and the right-hand side is a disassembled Somali. If you look at the arrows from left to right, it'll show exactly where the beginning of that line starts. There's different keywords that exist within Somali, like const-string is the same thing as a static string, constant string, static string. But going through all of this, if you go from left to right, there's almost a one-to-one representation. There are certain things like the test plus test2 for that string in the middle. On the right-hand side, it actually concatenates it together, so it's not exactly a one-to-one representation, but almost. APK tool is another tool that I use that is basically a wrapper for Somali and back Somali. It decompiles into a specific directory structure, but also handles resources and the Android manifest file. It pulls things down to a normal directory structure like that would exist in a normal Java project. It has a resources directory and a Somali directory. The resources obviously has all the resources that are in it. On the right-hand side is the directory structure of what the Somali directory structure looks like. The Android manifest XML file is actually parsed from another command called AAPT that ships with with the Android SDK. So that also is not a one-to-one representation, but usually this stuff can get, I haven't ran into a case where it was not able to recompile using APK tool. It also has the ability to install frameworks locally, and there's a debug mode, which I actually haven't ever tried to get working, but there's some videos online that show you can actually live debug Android applications in the Somali source. So set breakpoints in Somali, not having the full source of the application, and run it similar to just a normal debugger on a Windows machine, for example. Other tools that are going to be mentioned are Dex to jar, which converts an APK to a jar file, and JDGUI, which is obviously a Java decompiler. Those are used in conjunction to get somewhat of a Java source representation of the APK. Next on to analysis. Analysis is always separated into two separate types when I think about things. Dynamic and static. Dynamic is when you actually perform actions on the device, understand what's happening on the device, whether it's network communication, inter-process communication, or what files that are created and modified. And static, which is actually not performing any action, but looking at the files that exist on the machine or on the device, or the disassemble code, or the source code if you have it. It's typically not one or the other. When analyzing an application or doing a security assessment on an application, it's an iterative process going back and forth, as you'll see in some of the examples later. When doing dynamic analysis, the first thing that I typically look for is understanding the communication flow from a network perspective, and almost all of the time there is SSL being used. So knowing how to man in the middle of that is like step one when looking at this stuff. It also allows you to access the backend servers that it's going to communicate with. So when an Android application implements proper SSL communication, like this sample code down there, it will utilize the CA certs file that is located locally within the Android operating system. And if you're trying to man in the middle an SSL stream, you're going to have some sort of self-signed cert somewhere, and it won't trust that cert and fail closed, and it'll just get a Java SSL security exception in logcat output typically. But this is the first hurdle that you have to get over, is being able to circumvent that SSL check. And when it's implemented properly like this, the easiest way is to just install a CA onto the device locally. I'm hoping this demo is actually going to be big enough, but this is in Android 3 and below, this is how you would install CA locally on the device. It needs to be rooted in order to modify the system directory. So first thing you have to do locally on your machine is install the Bouncy Castle libraries by going to your Java home libx.ext directory. I'm just using wget to pull the jar down. That's what's used to package the CA certs file, or the provider that converts a cert to the CA certs file. You then use ADB to pull down the CA certs file from the device. Then you use keytool to create to import the CA that you want to install into the current CA certs file. As you can see, it's a very long command that I can almost never remember. It took me about 15 times to get this correct on the video. But that imports it. You say yes, you trust it, and now it exists in the CA certs file. You have to then remount the system directory so it's read-write on the device. That's why you need it to be rooted. It's because you need a root ADB shell. You run the remount command with the correct system directory. You can then change the permissions of the current CA certs file on the device. Then push the new one up to the device. And then finally change the permissions back, and then reboot the device. Can you guys actually see what's going on there? But, no, damn. There's a bunch of demos, and they're all this small, so that's going to suck. But I'll provide these slides somewhere that includes all the videos if ever anyone else wants to, if anyone wants to actually see what's going on. I don't know. It's a video, so yeah, it sucks. So previously on the emulator, you were able to install a CA certs file, doing a trick by copying the libraries so the emulator runs from a base set of system images that exist within the base directory of the type of operating system you're installing. But there was a way to copy them over to your local AVD directory, and it would run from there, and actually the changes would persist down onto that system directory. The reason you need these to persist is because when you reboot the device, if that system directory reverts back to its original state, your cert's not going to be installed. So it's very hard to, or it was easy to do this on an emulator by doing that trick and copying the system images over. Now, I don't know actually what version it changed, but it doesn't persist back down to that system image for some reason. That bottom link is a bug that I submitted. I mean, this isn't also important for security purposes, it's also for development purposes. You can do a lot of testing against backend infrastructure, for example. You're not going to have a trusted CA cert file or trusted cert installed on your device by default. The way to get around this now, if you don't have an old version of, I'm not sure if it's the emulator or if it's the firmware that actually is doing this, but I tried reverting back to an old emulator version and using the current firmware or the current SDK image, and it wouldn't work. So I'm being led to believe that it's more on the actual firmware that's writing these changes back to the image file versus the emulator that's taking care of that. But now if you do actually want to install this on an emulator, there's unyafs and makeyafs to image that you can do on the system image. Just like I was talking about before, copying it over and pulling it apart, installing the CA certs file, repackaging it, and then restarting the device. There's an option in OtterTool that I actually don't have a demo of, but it will allow you to create a persistent emulator or create a persistent AVD. So all the copying is done for you. You just have to. I haven't implemented this unyafs and makeyafs to image yet because it's all C code, and I have it working for OS X and Linux right now, and didn't want to compile different binaries. So in Android 4, they completely moved away from Bouncy Castle, and there's no single CA certs file. There's a CA certs directory in the same location. On the left-hand side, there's a directory listing of all the files that exist in there. I'm not sure what the IDs are, and I actually don't even have an ice cream sandwich device, so I wasn't able to test this. But I'm assuming that you can just simply, so on the right-hand side is an example of one of those files. It's simply a text file with X509 cert in it. I'm assuming you can just put a file in there and it will be trusted after reboot, obviously. But again, I don't have an ice cream sandwich device and wasn't able to test this, so it's more of an assumption. So the next problem that you usually run into with CA certs is even though you install the cert file onto the device, it's still failing for some reason. And that's typically because there's a custom X509 trust manager. But if anyone's programmed in Java before in SSL, there's a set of trust managers that are ran through to make sure that the server you're communicating with is actually trusted. There's the ability to override those. It's typically done by developers when developing against a development environment. That you're not going to pay for a trusted cert to live on your development environment. So what they typically do is just override the X509 trust manager chain and accept all certificates, which is obviously a security issue, but a lot of developers don't really understand what SSL is and why it's important. So this example on the bottom is a JD GUI, so Dex2Jar JD GUI of an APK that looks for, again, you can't really see it, I'm sorry, but It's the method within the trust manager is check server trusted. So it ensures that the server you're communicating with is trusted, and all it really does is checks to make sure that the issuer DN has the string VeriSign in it. As you know, you can create an SSL cert that has VeriSign in it pretty easily. And actually, the first time I was testing this application, I was using Mallory to do man in the middle, which was also created at Intrepidus Group. And it has the ability to dynamically generate certs that almost look identical to what you're communicating with, but so it looks like it came from VeriSign, except for the fingerprint doesn't match. So this was actually passing. It was working fine, but after looking deep into it, I found out that it was just looking for the VeriSign string, and with the X509 Trust Managers, you can include additional ones to the system ones, or you can completely override it and just have your own. In this case, it was just having its own. So the whole security of the Android SSL that was built in was just wiped away and replaced with, let me make sure this has VeriSign in it. Didn't work too well. So another demo of how you would actually bypass these checks using APK tool, and just all on command line again, so front row is going to be able to see. I'll try to tell exactly what's going on. So in this directory, we've got an APK called X509 modified SSL. First thing you have to do is use APK tool to pull it apart and get it into its Somali source or Somali representation. Then I just use grep to look through all the Somali for the string X509. That you will see that this one class implements the default SSL X509 Trust Manager. You can edit that file to find that check server trusted method. When you go down and you actually see the check server trust method, which is right there, you can see that it's checking for the issuer DN and seeing if it starts with VeriSign. If it does start with VeriSign, then it's okay. If it does not start with VeriSign, you'll see that it'll throw a security exception. So the method is of type void. So basically, if it doesn't throw an exception, it's trusted. If it does throw an exception, it's not. You can simply copy that return void and put it back above all the checks. So when this method runs, it does the initialization and then simply returns void. Adding that line circumvents all the checks. After you write that file, you use APK tool again to recompile this jar file into an APK, or recompile the Somali source into an APK. And then from there, you would think you could just install it directly back onto the device, but all APKs are signed. So you have to re-sign this somehow. You use key tool to generate a key store that you're going to sign this APK with. Again, a really long command line that is annoying to remember. All these examples I'm going to show at the end of how they can be done a lot quicker using Otter tool. But this is how you use key tool to generate a key store. From there, you have to sign the APK with the key store you just created, which you use jar signer. And then finally, you can uninstall the old APK and reinstall the new one. And then from there, the exception won't be thrown anymore, and you'll be able to man in the middle of the communication stream just as you were to normally. For those of you who don't know how to man in the middle, there's Mallory is a good tool to use, and Burp Suite. They all do handle SSL certs for you, and you can pull the CA certs from there and install them like I showed before. So here's a set of real-world examples of how this stuff actually looks in the wild and what I've seen and how I've gotten around it. The first example is a CRM system that we were looking at. A little bit of background on it. It had two parts, two APKs on it. There's an SSO APK that handled all the authentication portion of it and just there was no GUI associated with it. It was just like a service listening in the background, and a CRM application which actually handed the data coming in from the CRM, displayed it to the user in the GUI, and it communicated with the SSO and application in order to authenticate you when you started. It was obfuscated, as you can see on the right. It's just a set of classes that are just letters, which is extremely hard to follow. And it followed the common architecture that I was explaining before. It goes through an abstraction layer and has two backend components of authentication and the actual legitimate data store that responds back to the user device. When doing dynamic analysis, we were trying to understand the inter-process communication between the CRM application and this SSO application. In the manifest file on both of them, there was this Android protection level equals signature, which means that both the APKs had to be signed by the same signing authority for them to communicate with each other. Otherwise, that would throw a generic security exception. The communication flow that was happening is shown in that image in the middle. The CRM application would send an authentication request through an intent to the SSO application, which would forward it to the backend. The backend would respond yes or no, and if yes, it would give it a session token. The session token would be passed to the CRM application, and then the CRM application could request data directly from the backend. Both of those communication streams, or both of the communication streams from the SSO to the backend and the CRM to the backend were SSL encrypted, so you couldn't see them by default. Like I was talking about before, the first thing is to man in the middle of the network communication stream. So in this case, there's two actual communication flows coming from two APKs. The first one, obviously, we wanted to look at was the SSO application to understand that initial authentication piece. It was easy just by installing the CA, like I showed before, which would allow us to view the authentication that was being passed back and forth. The next step was to understand the communication flow from the CRM portion of the application, which was failing simply by installing the CA. It had the X.509 Trust Manager. It was actually the VeriSign one that I showed before, which would cause it to fail. Simply modifying the small source to return void for that check server trusted method would allow it to communicate, but when trying to run them, it just wouldn't work. It would fail with some generic security exception, which I didn't really understand until looking at the manifest file, which I showed before, that had the permission level of signature. And understanding that, I realized that I had to re-sign both APKs, not just the second one that I modified, by the same signing authority in order for them to communicate with each other. That's why that generic security exception was thrown. After that, I was able to view the communication stream and found one of the first flaws. This is a sample request when, after authentication, the CRM application would send this to the backend to try to gain some sort of, get some sort of data. And the key things to look at are the user ID and the transaction name. There's also the session token above, which was what was returned from the SSO application that allowed this to communicate. Or after the SSO, the single sign-on authentication, it would get a session token and injected in there. That's how it could presumably communicate with the backend. The response was just the normal, the header that was sent, and then the body of the data that was being requested. It's just a simple XML protocol. There's very basic, no XSDs or no SOAP associated with it. So one of the first things that I tried was to send requests directly to the backend to circumvent the whole middle layer. And notice on this request, there's no SM session token either. And I have the user ID of administrator, and sending that directly to the backend, going around that abstraction layer, was actually possible, and it worked. So this really doesn't have anything to do with the Android application, but it's the full infrastructure that exists that's associated with this Android application. And the main flaw that I think happened here was that the developers thought that every communication stream was going to go through this said process that was already put in place. But as we could see that I didn't go through that process and was able to actually call any function by any user without authenticating, which included changing passwords and getting contract information. That included customer data. It was all on the public internet, so it was kind of a serious issue. So with this vulnerability, there was able to run any transaction with any user without authenticating. It also had the ability to get customer data. In order to prevent this, I think the first thing is to not trust user application data just as if it was user data. I feel like it's like any web application. You're not going to trust the input from a user. There's a little bit more trust because you're developing the application, but there's nothing saying that I can't communicate directly with your endpoint. So don't trust the application's input because you don't know it's from the application. It's out of your trust level. There also should have been a link between the SSO application and the CRM application in the back end to ensure that when someone's communicating with it, that person is actually authenticated and able to get the data that they're requesting. This was all implemented in that middle layer, but that back end was still publicly available, so I could circumvent that authentication check or that authorization check. The other fix would be to block off that functional endpoint and the SSO endpoint and not allow it to be publicly accessible and ensure that everything has to go through that middle layer. So the second flaw, which is the first time I've ever seen this actually happen or actually working, was an XML entity inclusion. And this, for those of you who don't know about XML entity inclusion, there's a doc type node in the XML payload that basically is requesting a system file, and in this case, home admin SSH ID underscore RSA, which is the private key for the admin user. And then since the header was replayed to the user, you can reference that entity within the header, and it will, as you can see, replay that private key back to you. So from here, so I wasn't able to get that I didn't just guess and just say, I wonder if I can get the admin user. There's a set of steps that I went through to get that. First, pulling that C password file to understand the users, finding the Apache user, then finding the Apache home directory, finding the bin directory, then seeing that there's a start CRM script that shows that it was starting as the admin user, and then from there, found the admin user's home directory, and then the private key that exists. So with XML entity inclusion, it allows you the ability to list files, not just list directories, not just view the contents of files. But the key thing here is that just by hosting an Android application, you are, and having a vulnerability like this exist, you have allowed someone to gain access to your trusted infrastructure. You know, using this, they say this worked because they were using private keys to allow SSH authentication. How many other systems do you think have that same admin key in use? And also, do you think that backend server has to be trusted in some sense of the backend network? Because you know, the SSO application, for example, that's going to have to communicate with some sort of database to make sure that the user is authenticating properly. That database is not going to be just directly available to anyone. So you can see that it's very easy to pivot from this into the network and gain access to stuff that you wouldn't normally have access to. So the conclusion was that I was able to gain file system, any file as the admin user simply through an XML interface, and eventually was able to gain remote access to the server simply by having this Android application exist. You'll see a theme here of all the prevention measures is don't trust the application input. I don't understand why developers don't get that. Your request does not have to be coming from the application. It's just like SQL injection. I don't know. I can't seem to get this across to them, but yeah, don't trust the application input just as you wouldn't trust the user input, and obviously properly properly implementing XML-based APIs is a key to this one as well. So this is another example that is more of dynamic analysis that's related to a banking application that I was looking at. Before getting into this, I just wanted to, it's kind of an interesting, I tried reporting this to the vendor. I knew a person from an old job that works there as a developer, and this is the set of request and response, but the key to all this is the red section in the middle. It says, I was basically telling him, I have this vulnerability that exists in your production environment. Do you have a security team that I can communicate this to? His response was, according to the corporate policy and code of conduct of the company, I can't give you the contact information of any internal employee. I couldn't find anywhere on the webpage a security team to report to, so like, I don't know. I don't understand responses like this. But if you read through this whole thing, he was actually the developer for that interface, and I think what was really happening was he didn't want to get in trouble. So he was like, just tell it to me and I'll fix it, it's cool. I did, and hopefully got fixed, but yeah. So background for this banking application, it had the full functionality that you could do on the web interface, or basically in the physical location. View account activity, pay bills, transfer money, view credit card statements, and one key thing is remotely deposit checks via photographs. And to skip the whole man-in-the-middle portion of this, it was using SSL communication, obviously, but it was able to circumvent that just installing a CA on the device. There was this list.action that was the first thing I looked at. It was just a simple post with the list.action just basically gave your account activity. You needed a valid SM session cookie and a valid account ID, but there's this key type equals JSON that I was looking at and trying to play with. With this valid request, it would just give you a JSON representation of your recent account information, nothing special. So the first thing that I wanted to do was see if I could get that in any other representation. So the first thing I tried was XML, and got the generic Tomcat output showing me the backtrace of the error and showing that there's a file not found exception. Again, you needed all the valid information in order to do this. But as you can see, there's this in the red, it says failed to find a resource, and then gives you a file URL. And the last is xml.jsp. It's one key thing to note. The other key thing to note is at the bottom there is the Spring Framework backtrace. So you know this application was actually built in Spring. I have development experience in Spring, so I know that there's specific files that usually exist in these types of environments that may be beneficial to seeing. So what I tried was a directory traversal attack, and sure enough, simply having a type with a 101 directory traversal worked. Again, you need the valid credentials, but one thing about this, which I was actually looking for an application context.xml file, which usually exists in Spring in Spring web applications. It concatenates the .jsp to the end of whatever you're trying to view, whatever the type is, and so the failed resource says, the file not found exception says web inf and then application context.xml.jsp. So this one in itself wouldn't work because as far as I know, there's no null termination vulnerabilities in Java. But it's always going to concatenate that JSP and you won't be able to see anything. So this, I may have been looking at my legitimate bank account information to do this. So I wanted to stop right here and not really go any further. But if you put it all together, it seems very obvious that there's a high likelihood that there's an attack scenario here. It has the functionality to deposit checks through a photo, which means that you can upload images directly to this back-end system, which why wouldn't you just be able to arbitrarily upload files as well? There's also a directory traversal through the list.actions. I mean, the first thing that came to my mind was local file inclusion, and that's when I stopped and reported it. Again, my valid banking account credentials, so if you work for this bank, please don't get me in trouble. Thanks. So in terms of conclusion, there's a possible LFI, and don't hack your own bank. Again, the same that's been going through all the examples. Don't trust the application's input. It's like in this example, I wasn't the application, I was myself. And then obviously they had another vulnerability that existed, is just concatenating some string to access a file. 101 file, a directory traversal. Another thing I wanted to note is when doing all this, this always comes back to mind, is this Imperva data security blog, and they were analyzing the lulzsec attacks, and they said they were giving all the examples of the tools that they used to get this huge botnet and get into all these, hack into all these systems that they did when they were doing that stuff. And the first tool was RFI and LFI. I didn't realize how big of a deal this was until actually seeing this and associating with this, this blog entry. But I mean, that was their number one, from this analysis, that was their number one tool for gaining access to all these machines, which is pretty crazy to me because it's not something that is commonly talked about. But this is kind of just like putting it together that, this is a legitimate bank that has this vulnerability that exists. Imagine what else, I would assume that banks have more experienced developers than not, like lower companies that don't have to use all this proprietary information on their back end. I would assume that this exists a lot more widespread than people think. So moving to static analysis and some examples that I found. First is a little setup that I typically do when looking at things from a static perspective. Unzip the APK. An APK is just like a jar, which is just a zip file. You can pull it apart into its base files. Back Somali using APK tool to get the Somali files and the resources, and then dex2jar to convert it to a jar file, and then JDGUI to get a Java-like representation of the source. So the first example is a crypto-like example. Crypto is something that is always implemented improperly for some reason, just like SSL communication. And if I see this in an application, I will go directly for it. And it usually pays off 90% of the time. So this application has a remote management application that has the functionality to wipe, lock, locate your device from a web interface. The first thing that I think to myself is, how is this web interface going to communicate with the device to perform these actions? There's really two options, is somehow managing the IP address or SMS messages. SMS is usually the way that people implement this type of stuff. So looking at the Android manifest file, you can see that there's a specific class, .sms receiver, that gets all the SMS messages before they're displayed to the user. This Android priority that's shown at the second arrow shows that all SMSs are going to be processed through this class before they go and are displayed to the user. I was able to view a sample SMS by registering the phone, uninstalling the application, and then sending a command from the web interface. And at the bottom, there's a sample SMS, which is what comes through. It's a command, or in this case, lock, a colon, and then a random string, which to me looks like an MD5 hash. So looking at the SMS receiver, which was explained in the Android manifest of what processes these files, without having to show you the rest of the source, the broadcast receiver is the interface that's provided by Android that you have to implement in order to process this type of stuff. Then the application implemented a base SMS receiver, and then in this case SMS receiver. So in the base SMS receiver, the on receive event is what happens when an SMS comes through. You can see a little bit above that first arrow, there's a split on the colon, and then it has command equals, and then the first string, and then handshake token equals a second string, and it logs that out. So I know I'm in the right place. The next in the red is, it shows local application preferences get handshake token, compares that with a handshake token that was in that was coming in from the SMS. If those are equal, then it queues this SMS to be processed by this internal application. So the next thing was trying to understand where set handshake token is located within the application. Simply using grep through the source showed about 5 or 6 places. Every single one of them had the same source, which is this underneath there. The blue shows it's actually just looking, so the blue portion of the source is looking for the phone number in the local properties. The red is showing md5.util.generate MD5 hash string with the static string seedme plus the phone number. And then it's calling set handshake token on that value. So the, this guy's snoring up here. So the handshake token that this was being checked is just the string seedme and the phone number, an MD5 of that. So it's also checking every single SMS that's coming into this device, and as you can see, the command was static, and in the example I showed was lock. So I was able to basically just send an SMS from my phone with the right string to the phone that has this application installed, and without prompting the user fully wipe the device. So this is obviously a fail, but their secret or their crypto was the string seedme plus the MDN. Again, don't trust the input of the application. Another prevention would be to somehow filter on source numbers using external services that will actually send these SMSs usually have the ability to specify the source phone number of what's going to be coming in. And then why not use some sort of legitimate cryptography for this? Asymmetric encryption is built into Android. It's very easy to implement. So another example of static analysis is Skype has secret menus in it. For some reason, all mobile applications have secret menus built into them, and I don't understand why. And they're left in. They're usually like developer stuff, and debug stuff, but they're left into production builds, and I just don't get it. Again, weird developers. But background. The Skype application is very well obfuscated and it's very hard to follow. It also has a native code component. But when looking at the logcat output, I saw these messages that are highlighted. It's no config file name, mount SD card, Skype.properties. And I was thinking to myself, why would this application be looking for a properties file on the SD card? So started going back and trying to understand that. The first thing was to locate that Skype.properties string. Again, just using grep through the source, and the Somali was able to find it. But when grepping through this grep command was actually done through the Somali source as well as the Java source. And if you notice, the only thing that shows up is in the .somali files. It doesn't show up at all in the Java files. So this is another key when reversing these applications, is you can't always rely on the Java representation that's retrieved from JDGUI. I don't know if it's a fault in dex2jar or if it's a fault in JDGUI, but there sometimes are errors, and this is a great example of that. On the top, you can see the Skype.properties. You probably can't see, but I'll tell you. Skype.properties string highlighted in the blue within the Somali file, but at the bottom is that same exact method in the Java file that was decompiled using JDGUI, and it's just the commented out blue section it just has error above it, and it has some sort of other assembly lingo or bytecode representation of what is actually there, but for some reason the strings don't show up. So you actually have, if you want to do reverse Android applications well, you actually have to learn the Somali, unfortunately. So understanding how the Skype.properties file was being processed, the left-hand side is the Somali representation of where these strings were being looked at in the properties file. Luckily, it was just a normal Java properties file, so you look for a static string, and then you get the value of that string from the properties object. On here, you can see the first example. The top arrow is pointing to a login. The bottom is showing that it's putting a Boolean in some class after it does some sort of checks. So I know that this is of type Boolean for login, for example. On the right-hand side is a list of all of the different options you can put in this file. I Google searched to try to find if there's anywhere else that had information on Skype.properties. There's one blog or one forum question on the Skype forum asking about it, but there's no other information associated with it. So one of these options is debug menu, and it's a Boolean. So to me, that was the obvious thing to first check. So I simply create a Skype.properties file in the SD card with the contents of debug menu equals 1, restart the application, and pressing menu, you can see on the left-hand screenshot, there's a debug menu now available to me. Clicking that, there's these options for application log and Skype log, which are I'll show you why are important in the future, but on the second portion of it, at the bottom, you can see there's this weird button. It's emergency call American Airlines. I don't know why Skype wants to emergency call American Airlines, but it does call American Airlines. Not through Skype, through your normal phone. But apparently a developer had some problems with American Airlines. Who knows? But the important thing was these logging functionalities. Enabling those shows, it shows a ton of logging in logcat output. This is going to be, again, hard to see, but what's key to note here is that on the left-hand side, it shows you the exact class that these logs are coming from. This whole application was obfuscated very, very well and very hard to follow. But enabling these logs, you can see the class and the log output. Remember how we found the Skype.properties string, just grepping through it? That same concept can be used with this, except for the exact class that these logs are coming from. So you see send message. I know exactly what class send message is coming from, and it's probably what it's going to be doing. So it kind of takes away the whole need to follow this obfuscation that exists within this application. So the conclusion of this one is you can easily call American Airlines if you wanted to through Skype, but using your phone. And then the obfuscation is circumvented through this logging. And again, for some reason, developers like to leave all the debug logs, even though it's possible to remove them using ProGuard that has the configuration sitting there on new Android projects within Eclipse, but they still leave verbose logging and debug menus in there. Another prevention measure that doesn't exist yet in ProGuard, the free version at least, is obfuscating strings. The whole reason that we were able to get this Skype.properties file and see the processing of it was from grepping through the source for a static string. If those strings were obfuscated in any way, just simply cut in half and then concatenated later, we wouldn't be able to see that. So the other prevention is to somehow manually or use one of the paid obfuscators to obfuscate the strings as well. All right, so this is the tool that I created to circumvent a lot of the stuff to make all this stuff a lot easier. It's called AutoTool, and that's a little cat making his life easy. So remember when we were installing the CA, we had to pull down the file, remount the file system, add the CA to the CA source file, pull it back up, change the permissions, all that nonsense. In AutoTool, you go to Tools, Install Certificate, double-click it, and you're done. Makes my life a lot easier. So the X509 Trust Manager, which was when we were modifying that was looking for VeriSign, you had to pull the APK down, disassemble it, find where the X509 Trust Manager exists, reassemble it, re-sign it, uninstall the old one, reinstall the new one. In here, you simply go to the Somali menu, if it starts. It'll allow you to pull the APK directly from the device. And this, it's just, I think, com.1t. So double-click it. It loads the APK directly from the device. Clicking on the Somali tab. On the left-hand side will be the namespace representation similar to how it would exist in Eclipse, but search for X509, double-click, brings you right to the Trust Manager. You then have to go down to find the check server trusted, it'd probably been easier to just search for that, but you can see that it's searching for VeriSign, seeing if the issuer DN starts with that. If it does not, then it's going to throw an exception. If it does, it's going to return void. So copy that, bring it back up to the top, and paste it. So this returns void before any of the checks actually happen. Save the file, and this is the cool portion of it, is that it was always so frustrating to me to remember how to sign and build the APK, or sign the APK, create this, whatever I need to do to sign it, but these two options will sign it and generate the key store for you, and so that built the APK. And then there's a package manager which allows you to uninstall the old APK and then reinstall the new one. It also has the ability to mass uninstall, mass install, and mass pull. But from here, uninstall the old APK, and then, this is a slow demo, sorry. Install the APK, and you're done. So no need to mess with different command line options, any of that. Does it all for you. So there's another thing that I implemented in here that's been very beneficial to me for dynamic analysis local to the file system. I didn't really get into any of this in any of the examples, but it's a file system differ. So at 2 points in time, you can see what has changed in the file system. And I don't know of any way that this can be implemented. There's no find command locally on the device, but it scans the full directory structure, gives you a list of the files, and now I'm going to perform an action, simply do a Google search for AutoTool. And then it'll do a scan on the second time. The bottom will show you of the bottom of the application will show you that you can see the directories it's scanning through. And then when it's done, it'll generate the differences between the first scan and the second scan. So you can see what files have been touched, what files have been modified, what files have been added and removed. When it's done, the differences will be generated. Green is added, blue is modified, and if there's any red ones, it would be deleted files. So that's it. AutoTool is available on GitHub. Those are the links. There's TARS on the bottom link. The autotool.com is not actually working right now, but who wants to drink? So I think we have a few minutes if anyone has questions. No questions. I spelled otter wrong because my name is spelled with one T and otter should be spelled with one T.